Hello, everybody, and welcome to the next presentation at the Advancements in Thermal Management Digital Conference. I'd like to welcome our next presenter. She's the Applications Development and Laboratory Services Manager at C-Therm Technologies. Please help me welcome Sarah Ackerman. Thanks, Sarah.
Thank you very much for the introduction. So I'd like to first start by thanking everybody for coming to the talk today. I do appreciate your attendance, especially on trying out a new format here. So today, what I'm really going to be focusing on primarily is looking at a few different types of thermal conductivity testing techniques, specifically aiming at electronics and battery thermal management applications. So I'm going to start by discussing briefly about why thermal conductivity is important, and then go into a brief overview of some of the reliability prediction models out there, the importance of thermal management to reliability and reliability prediction, and talk about the role of thermal conductivity specifically in thermal management applications. I'll next go into how to get some good thermal conductivity data for input into reliability prediction models and thermal management design, which really boils down to choosing the right method and the right test conditions. And next I'll discuss a brief overview of a couple of common application case studies, and finish up with some conclusions. So talking about why thermal conductivity is important, on the left-hand side there, you can see a photo of a circuit board. And really, when we're talking about modern electronics, there's an ever-increasing drive towards making electronic devices smaller, more compact, but also more powerful, even as we make them smaller and smaller. And what that means is we are having more heat generating components closer together. So as we get more and more things that are producing heat in close proximity, thermal management becomes more and more important in terms of designing these devices for longevity and for good performance. The history of reliability statistics and reliability prediction comes out of some early work with electronics applications from the U.S. Department of Defense. In the early 1950s, I think 1950 was the first formation of the ad hoc committee, which later turned into a working group. There's a number of standards that exist internationally, including a military specification, as well as a civilian specification from Telcordia, which was originally a Bell Core specification from Bell Labs, as well as a few international ones, the 217 Plus and GJB standard from China. All models of failure rate prediction really have the same sort of concepts, even if they kind of stick them together in a different way. So I'm highlighting the one from the military specification here, MIL-HDBK-217, but there are, as I mentioned before, there's a number of other similar standards out there, and they all tend to have the same sort of elements in them, even if they're arranged differently. So in this case, we have the steady state failure rate for the unit being equal to some environmental factor multiplied by the sum of a failure rate, weighted failure rate for different individual components. So you basically take the failure rates for each of the components, add them up, and multiply by the environmental factor. And if you're looking at the individual components, these have factors including the electric stress factor. So how hard is the component being run compared to what it's been originally designed to work under, a thermal stress factor, as well as a quality factor. And for this particular talk, we're really going to focus mainly on the thermal stress factor there highlighted in red. So An important thing to understand about these models of failure rate is they're really focused mainly in this center area, the useful life span area of the lifespan chart here. So before that, you'll have immediately after launch a certain number of devices that are either have defective components or some other form of manufacturing defect, and they will fail early. And these are kind of referred to as your infant mortality on the failure rate curve. And at the end, you'll have another spike in failure, and that's basically when the device itself just starts to wear out at the end of its service life. But the failure rate analysis methods really focus on the useful life middle ground on this chart here. So I mentioned before about how we get the temperature factor, and it's basically based on the Arrhenius model. And so you can see that in the equation in the center of this slide. And so Arrhenius was a very famous thermochemist and kineticist back in the late 1800s. He contributed many things to the field of thermal analysis and kinetic rate analysis. One of the key ones among them being this concept of a rate constant or a rate law, which is where your rate of an event, in this case a failure rate, is proportional to an activation energy, in this case of the device or the component that you're looking at, divided by the Boltzmann constant multiplied by the temperature. And there will usually be some other constant involved here. But in short, the temperature factor is proportional to this activation function here. So next, we've mentioned about the temperature factor and how it will contribute to inflating the rate of failure if your temperature factor gets to be too high. So the next logical question is, how do you reduce this temperature factor? And the key one is through effective thermal management. So you need to maintain the operating temperature within the optimal operating range. So most devices have a certain range in which they were designed to operate. And if you go above that, your device will start to wear out more quickly. So thermal management is basically an umbrella term that includes a wide variety of strategies, but you can really break it down into two main areas. The first one is the design of active cooling mechanisms, such as forced air, cooling fluids and heat exchangers, Peltier elements, basically anything where you've designed a device specifically to pull heat away from where it's being generated. And the design of these strategies requires knowledge of thermal properties of the materials involved. Sometimes thermal conductivity, sometimes heat capacity, sometimes both. But it does require a firm knowledge and a firm grasp of the thermal physical properties that are relevant to the design in question. The next one is the design of passive cooling mechanisms. These are things like heat sinks, passive convective cooling, basically anything where you don't have to design and engineer a specific energy consuming device to achieve the end. So if it's just a heat sink with fins designed to encourage passive convection, that would be a passive cooling mechanism. And this will require knowledge of thermal conductivity and often knowledge of the environment that it's going to be operating in as well. A third component to thermal management that is becoming more widely used is material selection. So basically choosing your materials of construction with thermal management in mind, whereas before it might have been the thermal properties of the material were secondary, where you would look at them in your design after you chose the materials. Now, increasingly, even for parts that are not involved directly in thermal management, materials are being selected with thermal management in mind to some degree, basically trying to get components to serve a double duty. One, doing the thing that they're designed to do, but on a secondary basis, also help with the thermal management considerations for the design. So we've talked a lot about thermal management, but on the practical side of things, so I talked a bit about the theory of failure rate analysis, but practically, why is it important? And you can see some data as to why in a battery application. This data is taken from a paper in Applied Sciences published last year. And in this case, what they were doing was taking some battery cells inside of a calorimeter and charging and discharging them repeatedly over 250 cycles, and plotting how much how much heat energy was given off during these during the charge cool cycles or charge discharge cycle rather. So you can see here at the different temperature ranges, the cycle number is directly related to the degree of degradation of the battery system, but the temperature of operation also has a very large effect here. So compared with a operating temperature of 25 degrees, at 55 degrees Celsius, you have about 3, maybe even 3.5 times the amount of battery degradation after 250 cycles as compared to operating at a 30-degree cooler operating range. And this just shows how the thermal management is going to have a major effect on the lifespan of the device, in this case of the battery. A poorer thermal management, a higher operating temperature, is going to decrease the lifespan of this component. So we've talked about thermal management. I'm going to pivot a little bit to thermal conductivity. Specifically, thermal conductivity is a key property for thermal management design. And the reason is that basically thermal conductivity is the intrinsic material property when you're dealing with a pure material that governs the rate of heat flow in watts through a material of a certain thickness. Typically, this is measured in meters of a unit cross-sectional area when a known temperature difference is applied. So if you have a temperature difference of, say, 1 degree, that would get you the thermal conductivity of the material. So it's a measure of how efficiently the material will transmit heat energy over time. And so I mentioned before that it's an intrinsic property of a pure material is the thermal conductivity. But oftentimes when we're dealing with modern like composite materials and such, you might have something more similar to what you see on the right-hand side of the screen, where you might have this blue matrix and these black filler materials trying to make the more efficient heat pathways that you see highlighted in orange there. And the goal there is to basically, with the filler material, improve the thermal conductivity of the composite material relative to the performance of the pure matrix. And so if that's your goal, then technically speaking, if you want to be a physics purist about things, you're no longer talking in terms of thermal conductivity, because thermal conductivity is a pure material property. However, if your composite is made with a filler that's uniformly distributed, or if it's not uniformly distributed, if it's got a regular sort of organization to it, we can talk in terms of an effective thermal conductivity, which is usually symbolized by a K with a subscript EFF afterwards. And basically, you just substitute that number for where you would normally use a thermal conductivity number. talking about thermal conductivity, it depends really a lot of the material's properties. Depends on the physical phase. So if the material is solid, it will tend to have a higher thermal conductivity than a liquid. If it's a powder, the interstitial air is going to dominate your heat transfer. If it's a paste, usually the fluid that makes up the matrix of the paste is going to have a highly dominant effect, but the filler will also have a significant effect in the effective thermal conductivity. The structure of the material, this is especially important for composite materials. How well organized the filler is in a composite material will have a huge effect on the effective thermal conductivity. The composition of the material, the density, especially in the case of porous materials, and the degree of saturation will all affect the effective thermal conductivity of a material. So given all of those things affect the thermal conductivity of the material, how do we then get good quality thermal conductivity data? There's basically four main parts to getting good quality thermal conductivity data. The first one is trying to replicate the real world environment of the material. You'll see often from various manufacturers, they'll give a thermal conductivity number, but they won't necessarily tell you what conditions it was measured under. And that's an issue because most materials have a significant temperature dependence on their heat transfer properties. So if you're using a number that was collected at 25 degrees for a part that's operating at 80 degrees Celsius, you might have 30% error on that number simply because the number you're working with is not representative of the conditions at which the material will be actually used. So really replicating the real world environment of the material is key to getting good quality thermal conductivity data. The next one is to choose the correct method for the sample that you're testing. So if you're testing for example, a composite material, then you need to make sure the method you're choosing is going to be appropriate for a heterogeneous microscopic structure. And not all methods are appropriate for a material with a degree of heterogeneous structure on the microscopic scale. We do at C-Therm, we've published a free method selection guide. Feel free to mention it or to ask the question if you want us to send you that resource. It's available for free. I don't have time to get into today the ins and outs of method selection, but we do have that resource available for free if anybody is interested in doing some more reading. The third part of getting good quality thermal conductivity data is in reducing the effects of air between a sensor and a sample material. This is especially important in the case of solid samples. The effects of contact resistance, especially for higher conductivity materials like metals, can be a very significant source of error. So it's very important to make sure you're addressing thermal contact resistance when you select your method and your test design. And the fourth thing is you need to make sure that your experimental design eliminates the effect of other sources of error. Other sources of error will depend on the material and the test setup, but they can include things like convection, they can, either of the material itself or from ambient environmental drafts or what have you, thermal radiation, material phase change, any kind of chemical phenomenon going on, and in rare cases, sensor property changes. So all four of those are very key in terms of making sure you're taking those into account when you're collecting your data to make sure your data is applicable to the material and the situation at hand. So how does all of this apply to electronic systems? Well, electronic systems use a very wide variety of materials in their construction. You've got thermal conductivity ranging from low conductivity foams and aerogels, around about 0.03 watt per meter Kelvin or even lower, all the way up to very high conductivity metals or even carbon allotropes, where you might have a thermal conductivity of several hundred watts per meter Kelvin. So you might have 3 or 4 or even 5 different orders of magnitude of thermal conductivity within a single device for when you look at all of the different materials used for it. You also might have different physical states of material. You can have solids. If you've got liquid cooling, you're going to have liquids in the coolant material, and you're going to have paste from your thermal interface materials. You can also have different chemistry and chemical compatibility considerations. And for the non-solids that are being used, you can also have a very wide range of viscosity. And so one of the questions I get a lot in my role at C-Therm in the lab division is, well, what one method is going to test everything that I need and collect good data? And the short answer is none. There are some methods that are more versatile than others, and certainly there's methods that can do a lot, but there is no one size fits all when it comes to thermal conductivity testing. You really need to make sure you're picking the right method for the situation. So I'm talking about thermal conductivity test methods and choosing the right method. So I should probably talk about what they are. So thermal conductivity methods in general can be broken down into 2 main categories. The first one is the steady state method. These are very well proven, high performing, accurate test methods that tend to require fairly large sample sizes and longer test times and have a relatively restricted thermal conductivity range. But on the other hand, they are very high accuracy test methods. On the other end of the scale, you have the transient test methods. These are test methods where the measurement is taken before the material hits steady state. And in fact, the transient phase is specifically what is analyzed in order to get the material thermal properties. These could further be subdivided into non-contact methods like the flash methods, and also a few of the more niche thermal reflectance-based methods. And then the contact-based thermal conductivity test methods, which are over on the right-hand side here, of which the most common that are the most commonly applied include things like hot wire, needle probe, transient plane source, and modified transient plane source. So at this point, I'm going to get into a bit more detail on some application case studies. The first few will be done highlighting data collected using modified transient plane source test methods. So the modified transient plane source method uses a single-sided sensor that measures thermal conductivity and also another property called the thermal effusivity. Thermal effusivity is seeing a wide amount of application, particularly in the context of ASTM D7984, in terms of how it correlates with the human perception of warm feel and cool touch properties. So some folks who are interested in objective measures of human comfort perception might be interested in taking a look at that ASTM D7984 and some of the similar properties or similar research that's been done in the application of thermal effusivity to human touch perception. The MTPS sensor you can see on the right-hand side of the screen here. It's a single-sided sensor where the sample is set on top of the sensor probe in over this area here where you see my pointer. And the sensor has a basically a 2-part construction in terms of how the measurement is taking place. We have the sensor coil trace, which is basically a spiral of material with a high temperature coefficient of resistance. And then we have the guard heater, which is designed of a material with a very low temperature coefficient of resistance. So its electrical properties stay almost constant as a function of temperature. When we do a measurement, we'll apply power to both heater elements simultaneously. And the guard ring over here basically acts in a way to ensure that as far as the material over the sensor coil is concerned, the only thermal gradient is in the direction normal to the sensor surface. So that's what enables the one-dimensional thermal conductivity measurement and the measurement of the thermal effusivity of the material. Looking at some applications for the MTPS, specifically, we'll start off by looking at thermal interface materials. So some key performance attributes of these materials. You're going to want them to have a high thermal conductivity. If they cure, you want to have a low viscosity prior to curing, and if they don't cure, it's generally a good idea to have a low viscosity so that they flow and wet well. However, you'll want them to have a low volatility if they're non-curing materials like a paste, so that they don't dry out. They should be electrically insulative and chemically and thermally stable, and also have a high thermal diffusivity to enable responsiveness to what the device is doing. So generally speaking, we would recommend MTPS if it's a non-curing material, and a transient line source method if it's a curing material. So how do these materials actually work in practice? So generally speaking, they're applied as gap filler materials. If you think about having two materials in contact without a thermal interface material, if you zoom in at the microscopic level, there will be some degree of surface roughness, no matter how finely you machine a surface quality. And that surface roughness will impose an air gap, and air is a very efficient thermal insulator. Its thermal conductivity is around about 0.025 watts per meter Kelvin. To put that in perspective, the thermal conductivity of copper is about 400 watts per meter Kelvin. So because of that, air is going to pose, even a very thin layer of air is going to pose a very high resistance to heat flow. But if you fill in that air gap with something else, like a thermal interface material, this is going to lower your thermal contact resistance and greatly improve the efficiency of the heat transfer, and therefore the performance of, for example, a heat sink attached to an electrical component. So just to highlight some data on a thermal grease, this is some research taken from the International Journal of Heat and Mass Transfer. From some groups out of China, looking specifically at studying shape function or shape factor of filler particles on the performance of thermal greases. So the particles that they had included a nanoplatelet and a spherical particle, and then this kind of sharp and pointy shaped particle that they call a T-shaped particle, which is intended to improve the heat transfer efficiency and have a high aspect ratio. So to improve basically thermal communication between the filler particles. And so you can see on the right-hand side that their T-shaped filler particle performs a lot more efficiently as a thermal conductivity enhancer. So at the same volume fraction of loading, it has almost twice the enhancement of the next best performing filler material. So this just kind of goes to show the effect of the shape of the filler material on the thermal conductivity performance of a thermal interface material. The next set of application data we'll look at is looking at phase change materials. So phase change materials are materials that store and release heat on demand through a physical phase change. Typically, this is going to be a phase change from solid to liquid state and then back again, although some niche applications use other phase changes. So these are attractive materials in terms of their ability to store a lot of heat without changing in temperature very much. So that can be very attractive when you're looking to maintain the temperature of, for example, a battery or an electrical component within a certain narrow operating temperature range. This data is taken from advanced theory and simulations, looking at a phase change material thermal management system for battery vehicles, specifically lithium ion battery modules for electrical vehicles. So the system that was designed, you can see here in the upper right, this was again published by Farid Baharai's group back in 2018 in Advanced Theory and Simulations. And so specifically there's a lot of things that are attractive about phase change materials for battery applications and thermal and electrical vehicle applications, but there's a lot of challenges as well. They have a very unfavorable thermal inertia, which tends to limit the available latent heat and limit the kinetics of cycling of these systems. So the solution that was proposed in this work is to improve the thermal conductivity, improve the thermal inertia, and improve the cycling release, or the thermal cycling of the PCM material. And to do that, they needed to make sure that their composite PCM material would in fact have an improved thermal conductivity. So they measured the thermal conductivity of the composite material. And with about 10 weight percent of material loaded, filler material added, they had a very large improvement on the thermal conductivity, over 10-fold improvement. However, you'll notice that after the material melts, this effect disappears, and that's actually pretty common. Nanofluids will tend to have only a modest improvement on the thermal conductivity compared with a solid nanocomposite. But in the solid phase, the thermal conductivity is a more dominant and more important heat transfer mechanism. So it's not as bad if the material doesn't have as high of an effective thermal conductivity in the liquid phase, because convection can act as a heat transfer mechanism there. And they use this data in thermal simulations, as you see here. So you can see how thermal conductivity data is used to optimize the design and prove out a concept as having enhanced performance, even without having to physically prototype it in this case. The next highlight I'll look at is looking at dielectric papers. So these are materials that are often used to provide electrical insulation and also thermal management as a secondary performance attribute in electronics assemblies. And so this is some application data that can be used to verify performance of maybe a new lot or a new batch relative to a specification. You can also use the MTPS because it has that one-dimensional measurement that I mentioned before. You can use it to test anisotropic materials. Specifically, in this case, you would reorient the sample so that the direction on which you want to measure is normal to the sensor surface. And on the right-hand side, this is some practical data that was collected on an FR4 board, looking at the in-plane thermal conductivity and the through-plane thermal conductivity of that material. This next set of data is looking at a transient plane source sensor. So this sensor uses a bifiller spiral that's encapsulated in a dielectric material. It offers a lot of flexibility for the user in terms of selecting their experimental parameters in terms of test time and power. But also the onus is on the user to make sure they're using the method correctly and designing an experiment that is valid for the material that they're working with. So the first set of data we'll look at is a thin films utility for TPS testing. This is a method that's best suited for low thermal conductivity samples, particularly unsupported thin films. So when you're testing these kinds of materials, what you do in practice is take a first blank, and then you can measure a layer of the material. And if you wanted to just have a higher level of certainty in the performance or in the test data, you can add a couple of extra data points of additional layers just to make sure, add more data points for that linear regression that we use to determine the thermal conductivity of the material. Here's some practical data that was collected on these kinds of materials. So you can see here, we've got Nomax, Kapton, Mylar, polypropylene, and cellulose acetate, all those materials that are tested using this method. So with TPS, with this style of sensor, there are several different algorithms. I've showed you the thin films algorithm that can be used with it. You can also look at a method called the slab algorithm, which allows you to test higher thermal conductivity materials that have a finite thickness, but behave like they're semi-infinite materials in the in-plane direction. This is really useful for looking at things like thin metal sheets and metal foils, which is actually the application data I'll be showing in the next slide after this one. When you're testing with this, you sandwich your two specimen halves around the sensor, and then typically you'll apply an insulation material above and below the specimen halves. Or alternatively, there are some other ways in which you can support the samples around the sensor. But the goal is always to make sure that as far as the heat flux is concerned, it hits a wall and can't transmit in the through plane material once it hits through the thickness of the material. So after the initial region penetrating through to the far boundary, all of the heat transfer is in the in-plane direction. This is looking at measuring an aluminum foil that's 0.13 millimeters in thickness. So this aluminum foil was pure aluminum, 99.9%. So we're referencing this to the thermal conductivity of pure aluminum. And the difference between the two is less than 2%. So it has very good performance even on very, very thin materials like these aluminum sheets. And then also with a TPS system, you can also test anisotropic materials. In this case, you sandwich the sensor between materials that are specimen halves that are thick enough to act as semi-infinite mediums. And then if you have knowledge of the volumetric heat capacity of the material, you can basically solve for the through plane and the in-plane factors of the thermal conductivity. And so that data you can see here, looking at Lexan, PMMA, and Garolite samples. So in all cases here, the test data is within better than 5% of the reference data. And so in practice, if you're looking at a test on an anisotropic sample, this is what it would look like. But basically, in conclusion here, what we're really trying to get across is that the accurate thermal conductivity data is key to the quality of your electronics thermal management design. If you don't have accurate thermal conductivity data, the models that you're using to design your material are going to be incorrect, and therefore the designs might not be as optimal as they could be. And ensuring good quality thermal conductivity data really requires choice of the correct test method for the material and the conditions, the correct test conditions to properly reflect the real-world application conditions of the material, and the correct sample preparation. So if your test method, for example, requires samples to be very flat and your sample is bowed and you run a test on it, you're probably not going to have good quality data being collected. Transient techniques do offer a lot of versatility to test a wide variety of samples. If you're using some transient techniques, many of them have a dynamic range in their thermal conductivity measurement range of 3 or 4 orders of magnitude. So they can be very versatile and very powerful in terms of characterizing materials for you. But that said, no one method is going to be appropriate for all samples. The correct approach is kind of a holistic approach that picks the correct method for the material and the test conditions at play. Transient methods do offer, however, very accurate thermal conductivity methods and offer a great level of flexibility to test your samples under conditions that will be relevant to your final end use application. And so that basically brings me to the close of my talk. So thank you very much again for coming out and listening to me talk for 40 minutes, I guess. I'll turn things back over to Nick for the time being.
Yeah, and if you'd like to take any questions, you do.
Yeah, sure. I'll just go over to our application page here. Yeah, so there's a question about receiving the slides after the presentation. Nick, do your folks distribute the slides after?
Yeah. So we can distribute the slides. It'll be available in the upload section.
Perfect.
Of MeetMax.
Yeah, Jose from Cornell is asking, how do we get uniform distribution of fillers in a composite thermal interface material? That's a really good question that a lot of research has been devoted to out there. The short version is that it really depends on the type of thermal interface material and the filler chemistry. There's been some work out there using sonication mixing, some that use planetary ball mills to improve mixing. And a lot of groups use surfactants and other kinds of additives to the mixture to prevent clumping and agglomeration of the particles. But it is a really good question. Few requests for this selection guide. I'll follow up with those of you who need that later. There's a request for a title of the mentioned paper for measurement methods of heterogeneous materials. So I'm not particularly sure which paper you're referring to. If it's the method selection guide, I'll follow up with you after. And I will follow up on I'll provide you with a link to the method selection guide as well. Some folks have asked if the material geometry has to have the same dimension as the hot plate for MTPS. No. If the material has a thermal conductivity of less than 100 watt per meter Kelvin, it simply needs to be larger than the diameter and of a certain minimum thickness that's dictated by the thermal conductivity. So I'll follow up with that person later. Regarding, I think we're starting to run a little low on time. How much, do I have more time to take another question or two?
Yes, there is time to answer a few more questions. We're up against lunch, so if you want to answer a few more, that's just fine. Okay, great. With regard to the best method for filled TIMs, that's going to depend on the nature of the thermal interface material in question. If it's the kind that kind of cures in place like basically a thermally conductive glue, you're probably going to want something with a robust sensor like a
transient line source so that the material can cure around the sensor without having to or without causing damage to the sensor material. And then for materials that are more flexible and flowing, we would usually recommend the modified transient plane source method. There is a question about why some of the photothermal methods are not used, and that's in my case, that's because in the context of electronics and batteries, a lot of the photothermal methods make the assumption that the material is a pure substance, and that it's isotropic, and that is not typically the case when you're dealing with most battery materials. So if you test a sample on a photothermal material, for example, or on a photothermal test method like a flash diffusivity measurement, there will be error introduced by the fact that the material does not meet the core assumptions of the test method. However, there's other photothermal methods that we actually do use on an internal basis, like using a photothermal camera, like is mentioned here, like an IR camera on cycling. And that's a very good complementary technique. Like it's also a very good approach. This talk is focused mainly on thermal conductivity methods. And the only reason I didn't mention the IR thermography types of methods with IR cameras when you're operating the device to spot hotspots is just because it's outside of the scope of the talk, but it is a good approach. I think, yeah. So I believe that we're out of time at this point. So what I'll do is I'll follow up with folks with additional questions. Either myself or some other folks from my group will follow up with all of you with additional questions after offline, just because I don't want to keep anybody from their lunch for too long. I'm happy to sit because I'm in the Eastern time zone and lunch for me was about 2 hours ago, but I'm sure some of you are probably going to be getting pretty hungry. So I guess I'll let folks sign off for now, and I'll follow up with those of you who have questions offline after the talk.